Hi, today we're going to be looking at how the frequency response of the RLC parallel circuit looks like. So, we saw the circuit looks like this, and we calculated in a previous video our transfer function that looks like this. So, now that we have our transfer function, what we're going to do is substitute S by j omega so that we see the frequency response, and then calculate the magnitude and the phase. And we're going to use again the 3 points to evaluate it analytically, which is for very small frequencies, at a very high frequencies, and at my resonant frequency, which is 1 over square root of LC. So the first thing we do, we substitute by S by h omega. So my transfer function will become j omega over R1C over j omega squared plus j omega times 1 over R1C plus 1 over R2C plus 1 over LC. So, now, first we're going to calculate the magnitude. So, let's calculate the magnitude here. The magnitude of j omega, of h of j omega, is the magnitude. So, I'm going to write it like this. So, we calculate the magnitude of this, and it will be the magnitude of all this. So, we have a quotient, and the magnitude of a quotient is the quotient of the magnitudes. So, I'm going to write the magnitude of this over R1C over the magnitude of this. Now, this j omega squared becomes minus omega squared because j squared is minus 1 plus j omega times 1 over R1C plus 1 over R2C plus 1 over LC. So, the magnitude of a complex number is the square root of a real plus the square root of the imaginary and the squared of the real plus the squared of the imaginary and square root of that. So this is purely imaginary, so the magnitude of an imaginary number, it's the number. And so, on the numerator, we get omega over R1C. And on the denominator, we have these two numbers are real, and this is imaginary. So, I'm going to write the real, so square root of the real part squared. So I have 1 over LC minus omega squared, and that squared plus the imaginary part, which is this one, omega times 1 over R1C plus 1 over R2C. And so I'm going to put squared like this. So this is my magnitude. Exactly. So now I'm going to calculate the phase here on the right. So I have the magnitude here. The phase of this so my phase of h of j omega is equal to the phase of the numerator minus the phase of the denominator. So this is going to get long. Is the phase of the numerator. The phase of the numerator, which is j omega over R1C, minus the phase of the denominator, which is, again, minus omega squared plus 1 over LC plus omega times 1 over R1 plus plus 1 over C R2C. So it's all this phase. So the phase of a complex number is the inverse tangent of the imaginary over the real part. So I get the phase of this number. This is an imaginary number only. The real part is 0. So I get a tan of the imaginary part, which is this, over 0. And then here minus the inverse tangent of the imaginary part, which is this, omega times 1 over R1C plus 1 over R2C over the real part, which is minus omega squared plus 1 over LC. So in this case, this number becomes infinity, so the inverse tangent of infinity is 90 degrees. And it's positive, I believe. So it will be 90 degrees minus whatever comes out of this number. Omega times 1 over R1C plus 1 over R2C over minus omega squared. Sorry, this is all omega 0, isn't it? Plus 1 over LC. So this is the phase. And what we would usually do is try to calculate numerically or approximately what the values for the transfer function would be, the magnitude and the phase that we have here as well, when I have a very low frequency and my resonance frequency and a very high frequency. So I have calculated that for you here, and the details of the calculations are in the script. You can find them there. So we can see that from the transfer function that when omega tends to 0, the magnitude of my transfer function tends to 0 and my phase tends to plus 90 degrees. When the omega is equal to my resonance frequency, the magnitude of my transfer function tends to be the value of my voltage divider and the phase tends to 0. This is because when I'm at resonance, the impedance of these two elements cancel each other out. That's the definition of resonance. And therefore, the output voltage is just the voltage divider between these two resistances. And lastly, when omega tends to infinity, my magnitude tends to 0 again, and my phase tends to minus 90 degrees. Now, if we simulate such a response of such a circuit, we get this response here. So this is our frequency response. As we mentioned in the step response part of the video, the response will basically depend on the damping factor that we have. Here I have many curves plotted with many damping factors. This curve here, which I don't know if you can see, but it's the thick one and it's the color blue, corresponds when zeta is equal to 1, so it's critically damped. And when my zeta, and this one here for the phase. So what happens when I increase zeta, that means my damping factor is bigger, it basically broadens my peak here. Yeah, it broadens the peak, and it makes my phase response flatter. Yeah, when I decrease my damping factor, then my resonance is sharper, so I get a stronger peak. It doesn't increase in amplitude, but it's sharper. So the Q factor, which is basically a measure of how thin my peak is, becomes higher, because when my Q factor is higher, it means that my peak is thinner, and my phase curve becomes sharper at resonance here. So yeah, that's what happens. Now, it does make sense with what we just calculated, that when my frequency tends to 0, my magnitude tends to 0, and when my frequency tends to infinity, my magnitude tends to 0 as well. So we get this in a graph like this. So every time we have a resonance, an RLC parallel circuit, we will get one response that looks like this, and exactly which one will depend on the value of zeta, which depends on the values of the components we choose. So in the following videos, we will look at the frequency response of RLC series circuits. Thanks for watching.